Okay, good morning, everyone. Uh, I have a good questions on chat. Any other questions that you guys have from the homework? Okay, I first address the question that your classmate asked me, which is the following. When I take the span of anything, and in particular, she asked about a vector. So if I take the span of a vector, okay, your classmate. Yes, I will. Okay. The question is the following. I want to see if anybody can answer her question. She told me why I've said in class it's the line through the origin. And her question, why the line has to go through the origin? Uh, can anybody answer the question? Why zero is on the span? Why zero is on the span? Anybody can answer her question. Why we have zero? Why zero is on the span of you? You can, yeah, because the tail of the vector is from the origin. I actually would go more with Jackson's answer. That's really the correct answer because the zero is zero in the span. And the answer is yes, zero in the span. Because zero could be written. So zero times u. So it means zero is in the span. So 0, 0, the pair 0, 0 is one of the span. And zero vector, we visualize it as the point 0, 0. So since 0 is 0 times u, 0 is in the span. So this is in the span. It has to be in the span. Haley, is the answer making any sense to you? Yeah, thank you. All right, so that's crucial, the zero in the span. Now, anything else in the span? So actually, I was planning to start the lecture with that, but I see other questions. I will answer them. So, uh, so the span of u, so suppose u is the vector u1, u2, it means u is this one right here. So this is basically for me u1, u2. And to be able to scale a vector, so I usually put those points just to make sure that when I tell you what 2u is, I can draw it. So 0 is absolutely in the span. This is right there. Another thing in the span is, of course, u1, u2. And then 2 times u. But where is 2 times u? If this is u, and as another one of your classmates said, all the vector go through the origin, when you're going to scale it, you're going to still live in here. There is no way else. That's going to be 2u. Means this point will have for coordinate 2u1, 2u2. This point will be, this point will be, this point will be. So the span will have to be a line. So I will go over number 13, of course, and then I will go back and start the lecture. So number 13. If anyone has any other questions, please feel comfortable. When I'm gonna go back, I hope, I keep my finger crossed that I will be back, I think 11 in your class, February 11. That's really my hope. Uh, let's see, this is January, February. Yes, I'm hoping that February 11 I will be with you. It means not next week, the week after. That's really my goal. Okay. All right. So now I'll go to number 13 and then we proceed. So here's the question. They gave us a matrix. And the inside of the matrix are 1, -4, 2, 0, 3, 5, and -2, 8, -4. That's A. And then B is the following vector. 3 minus 7 and minus 3. All right. And the question is, determine if B is a linear combination of the vectors formed from the column of the matrix A. So what do they mean by that? This is the first column of A. We call this, let us say, V1. And this is the second column. We can call it, let us say, V2. And this is a third column. And I will call this V3. And the question is the following. Is B, it means this vector B, a linear combination of the columns of A? It means of V1, V2, and V3. Now that's the rewording of the question. So which is basically equivalent to ask you the following question. Can I put some weight on V1 and weight on V2 and weight on V3 so that the sum of this combination will give me the vector B? So this is really the question. I mean, is this possible? So it's equivalent basically to solve this equation. All right. And now we solve it like we did last time. So it means this is equivalent to solve the following. C1, I have to start switching to pencils so I don't do mistake. 1, 0, minus 2. So can I find those? Those are my unknown. 2, 5, minus 4 equal 3 minus 7 minus 3. So that's really what we have to solve. So now this is equivalent to solve the following. If I add the left side, I set it equal to the right side. This would give me 3 minus 7 minus 3, and the left side give me C1 minus 4C2 plus 2C3, and this will give me 0 plus 3C2 plus 5C3. So we're actually now having a system that we need to solve. Minus 2C1 plus 8C2 minus 4C3. Okay, so the question is, can I find those C1, C2, C3 so that this vector will be equal to that vector? So this is equivalent to solve the following system. C1 minus 4, C2 plus 2, C3 equal to 3. And then 3C2 plus 5C3 equal minus 7. And finally, minus 2C1 plus 8C2 minus 4C3 equal minus 3. And now it's a system, a simple system of 3 equations, 3 unknowns. So the only way to do it is to solve it. And as I said last time, we should know the augmented matrix of the system. So the augmented matrix will be the coefficients of C1 are nothing more than the entry of the vector V. So this is what we have here. This is right there. That's the entry of, so this is going to be V1. This is going to be V2 because that's where the coefficients of the unknown C3 are coming from. And this is 2, 5, minus 4. And finally, 3, minus 7, minus 3. So the whole problem will boil down to solve this. And now we have to solve. Now, did anybody solve the problem? Did anybody solve it? Usually, my student, the way I always started that, they will usually give me the echelon form, so we don't waste a lot of time doing it in class. Anybody has the echelon form? Anyone? So please next time be ready with the echelon form because I don't really want to waste time on it anymore. So that's going to give me a 0. I have my 0. 2 minus 2, I'll have a 0 in here. I multiply this by 2 minus 8 plus 8, I'll have a 0. I multiply this by 2, 4 minus 4, I have a 0. I multiply this by 2, 3 minus 6 minus 3, 6 minus 3 will give me a 3. Do I need to go on any further? The minute you see that, do I need to go on and solve? Absolutely not. I have a pivot right here. Okay, so it means the last row read. So I really don't need to go on last row read. 0 C1 plus 0 C2 plus 0 C3 equal to 3. It means the system inconsistent. System inconsistent, it means B is not, there is no way I can write B is not a linear combination of the vector V1, V2, V3. It means the column of A. There is no way I can reach B. So this is a vector. We're all in R3 in here. So whatever this vector is, whatever the vector is, it should be down here. That's my B here. There is no way I can move a little bit in the direction of V1, a little bit in the direction of V2, a little bit in the direction of V3 and reach the vector B. This is really impossible. And very soon you will understand what is the picture, why it's causing this, why I cannot reach B following V1, V2, and V3. There is a reason why this cannot happen, and it will be clear, hopefully, in the next 2 weeks. And any other questions from the homework? Please make sure you do them even if I'm not with you. So we're going to work a little bit with the span today, a little bit more, and then we move on. So last time we talked about the span of one vector. So it's basically a line. And sorry. Okay. And then I started mentioning a little bit span of two vectors. I'm going to talk a little bit more about that. So span of two vectors. Of two vectors in R2. Okay, so let us recall what I did last time. Okay, what we did last time was the following. I start giving you a fairly simple example. So I told you I take the following very particular vector, 1, 0, it means disordered pair, and 0, 1. And we drew the picture, and 0, 1, 0, 1 as so that was 1, 0, and this is 0, 1. My question to you was very easy. I told you if I take any point here, anything here, can I write it as a combination of 1, 0 and 0, 1? And everybody told me yes, these are nothing more than the component. So it's 2 times 0, 1 plus 3 times that. Okay, so this means the way we interpret that, the way I told you interpret that, it means that anything here, any vector in R2, it means if you take any ordered pair, whatever the ordered pair are, you can write them as a combination of those two vectors. Mathematically, we express this by saying that the span is R2. Which means to you, which is usually a hard concept for us, which means to you is the following. If you take any ordered pair of numbers, you can write them as a combination of this vector and that vector, any pair regardless what it is. Now, question number 2, again, we did last time was the following. I took those two vectors, 2, 1, and minus 3, 2. Okay, and we did the same picture, 2, 1, 2, 1, That was this one. And minus 3, 2. Okay. And my question was, and I think I assigned a homework along those lines. So this is the line carrying Q, and this is the line carrying V. This is my U here, and this is my V. That's what I mean. And my question was the following. Geometrically, at least geometrically, is the span equal R2? Is the span equal R2? What do I mean by that? It means if you take any ordered pair of numbers, anything here, doesn't matter what they are. So anything here, any A and B, can I write them as a linear combination geometrically? And our answer was yes. If this is your vector, you can take a line parallel to V, like this, and then till it hits the line U. And then you can write this as a linear combination. So geometrically, anything in R2 can be written as a linear combination. Now, how do we show this algebraically? Algebraically, because the geometry, we can do it in R2, we can do it basically in R2. Once we hit R3, we don't see the picture as clearly. So algebraically, how do you convince me that, so how do you convince me that the span equal R2? Okay. It means you have to tell me that algebraically, that if you take any ordered pair, you can find weight such that this ordered pair is a combination of this ordered pair and this ordered pair, or this vector and this vector. So the way we proceed is like this. We start, we take an arbitrary vector in R2. Any vector in R2. Anything. Okay. And we have to show that this vector, this any vector, h and k are any, and now we show that hk is a linear combination of 2, 1 and minus 3, 2. So that's how we show those kind of ideas algebraically. It means we have to show that this equation equal hk has a solution. Is you can all, regardless of what h and k are. So we can show that this has solution regardless of h and k, of the values of h and k. Okay, so algebraically, we have to show that anything in R2 is a linear combination of 2. We take arbitrary vector and we show that this equation will have solution regardless what we put here and here. So how we proceed here? So we want to solve the system. So this is equivalent to solve the system with augmented matrix. So we want to solve the system and we show with the following augmented matrix. So the augmented matrix would be, will be the vector that I want to show it's a linear combination, and these are the vector minus 3, 2. And now the idea is to show that this has solution regardless, whatever h and k, there is a solution of the system. So how do we show that? We solve the system as usual, and we try to argue, does the solution exist? So we're gonna solve the system. Okay. So I would first start by changing rows just to have a 1 here, which make things easy for us. So I change everything. I have my 1. I want to make this into a 0. And whenever we have parameter, when we're solving a system, we only stop at the echelon form. We never go to the reduced echelon form. It makes it much harder. -2 plus 2, it's a 0. So I would take -2 R1 plus R2 into R2. -4 minus 3, sorry, -4 minus 7, -2 times K plus H. Okay. Now I address the question to you, and I hope you guys will answer. Will the system have a solution, regardless what H and K are? Means if I put any number here, can I always find a solution? Absolutely. Anybody else beside Haley? Yeah. Why we can find a solution? First, there is no way I can, so this system consistent, regardless, no matter what H and K, for all H and K. Now you can give me all kind of reasons. The simple reason is because there is no row, there is no way you can, no row of the form 0, 0, non-zero number. The reason is I have a pivot there is no pivot. There is no way we can have a pivot in the last column. I have 2 pivots in the row 1. I have a pivot in row 2, and they both occur in the coefficient matrix. There is no way I can create an inconsistent system. So algebraically, this means that regardless what you give H and K value, we can always find C1 and C2. Actually, in this case, let us note here, you don't have to write this, but just to convince you, from here, I can deduce that C2 is always, I have it. That's going to be the C2. I really have a real value for C2, and C1 do back substitution. Back substitution. Okay, so this is algebraically where everything works. So in R2, of course, so we have this situation. So now I will ask you a question, and then we have some kind of a simple rule. Question is the following. Okay. Describe, I want you to read the question carefully and the vector I'm going to give you. Describe the span, so I'm still in R2, of the following 2 vectors. I give you a few seconds to look at them and provide me with an answer. And please, I want all of you to participate, all of you. Think geometrically a little bit. Draw the vectors the best you can. Anybody can notice anything with those vectors in the relationship between them. Since the vectors are collinear, the span is just a straight line. Absolutely correct. Watch how I gave you the vectors. If I call this U and this V, watch from here to here, I multiplied by 2. From here to here, I multiplied by 2. So there is a common multiplier between the component. So this is really going to give me that the vector V is actually a scalar multiple of the vector U. So V is exactly 2 times the first vector. So the vector V is a scalar multiple of the vector U. So now when I'm going to find order linear combination, 0 is absolutely in the linear combination because of what we discussed at the beginning of the hour. The vector 2, 1 is right here. That's the vector 2, 1. V is nothing more than a stretch of 2, 1. So basically, this is my V. So V is absolutely right here. So this is my U, and this is my V. So now whenever I take a combination of them, so I take, let us say, 2U plus 3V, 2U plus 3V is going to be on the same line. So we're not going to leave that line. So the span is the line through the origin and the vector U. Now, the language is a bit confusing, and let me clear it up. When I say the line through the origin, it means I mean the line through the point 0, 0. The book will use this notation, but let us understand it. And the line through U, what really we mean is the line through the point 2, 1. So even we use this notation, but the idea is it's the line through the origin and the point 2, 1. That's really what the book means, and that's what this notation means. Very good. So now we're going to state a very simple theorem, and purely intuitively based on what we are saying. So we have the following result to understand the span of 2 vectors. So I will start and I will leave an empty spot that you guys have to fill up. Okay, so let U and V be 2 non-zero vectors. Any non-zero vector. Then, under what condition the span, it means if I take any linear combination of them, I will get everything I want in R2. What shall I write here, do you think, for the span of those to give me R2? So I have those 2 vectors, U and V. What condition should they satisfy? So when we find the span, should the answer be written in terms of the coordinate of the vectors? I'm trying to understand your question, Haley. I'll get back to it. Let me finalize this. Okay, then let U and V be 2 non-zero. Then if U or V is not scalar multiple of V, if U is not scalar multiple of V, then the span is equal to R2. Exactly. So we got the span. Everything in R2 is a combination of those, as long as those 2 vectors are not a scalar multiple of each other and of the situation. So 2 vectors in R2 or 1 vectors, the span is not really hard. It's just basically every linear combination, but to visualize it, for 1 non-zero vector, it's a line. For 2 zero vectors, as long as they are not scalar multiple, you can reach anything in R2 by combining 2 vectors. All right, so now we're going to talk a little bit about 3 vectors, and we cannot do much more. So now, span of 2 vectors in R3. So first, let me note here something, that when you are in R3, means right here, any 3 point, as long as they are not collinear, they form a plane. All right, so any 3 point in R3, that aren't collinear form a plane. Form a plane. Okay. So now let me ask you, let me consider the following problem. Suppose U and V are two vectors in R3. Such that U is not scalar multiple of V. So the question is, what is their span? So let me draw a little bit the picture. U and V are any two vectors. So this is my U, and this is the V. This is U, and this is V. Okay. So first, what is the span of U and V? So the span of U and V is basically all linear combination of UV. Okay. It means all vectors of the form C1U plus C2V. Every vector that I can obtain this way. So now a little bit geometrically, what's going to be the span of UV? So R3, no, not R3. No, two vectors. Let us think a little bit about it. Question number one, is zero a linear combination? I've asked this question several times to get it clear. Zero is a linear combination because I can write it 0U plus 0V. Okay. Part two is U, of course, is 1U plus 0V is vector in it. If I stretch U a little bit, 2U is also in the span. So everything on this line right here is going to be in the span of UV. And the other thing on the span, V is in the span. Half V is in the span. This one, everything here is in the span. But what are all those vectors? What are they going to be? It's not R3 at all. What's going to be? So everything in the span is obtained this way. How can I get it? I start 0, I stretch U a little bit, and then I move a little bit parallel to V, and I stretch it. This is a vector in the combination. Another vector in the combination, I can start from here, draw a little bit like that, in direction of minus U, a little bit in the direction of V, I get that. So try to a little bit imagine which vector do we get by doing all this. So you have those two vectors here, those are your vectors, and everything I take, any other vectors in them is that obtained. Start from here, you stretch this a little bit, and then you move in the direction of that. This is the vectors you're getting. So let me ask you the following. Look at my finger here, and look at this span above it. Is there a way to reach the top of my pan by following the direction of U and V? Do you think you can reach the top of the pan following the direction of U and V? Can you move a little bit this direction? Absolutely not. So now think a little bit what's going to be the span. A plane. It's going to be a plane. So we're going to do P to be the following. Let P be the following plane. Let P be the plane that contains the following. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, 119 I mean this point right here. U, I mean that point right here. V, I mean really the tip of this right there. Because U and V are not scalar multiple, it means that 0, U, and V are definitely not collinear. So this is the plane containing 0, U, and V. So the span of the two vectors, U and V, so the span geometrically of the vectors U and V is going to be actually, of course, all vectors of the form. That's algebraically of the form C1U plus C2V, and geometrically, that's going to be the plane P. That's the only vectors that we can. So if we take the plane here, that is formed by V, U, the span is going to be exactly that plane. Anything in that plane, like we did in R2, anything in this plane, I can reach it by going a little bit into direction here and a little bit like that. So basically you're thinking of like basically the plane and you are tilting it a little bit. So everything in this plane could be written as a linear combination. Once you have a vector outside the plane, there is no way you can reach it by following U and V only. So the span of two vectors in R2 is going to be actually a plane, as long as the vectors are not linear combination of each other. So to get every vector in R3, I actually need 3 vectors. And this will be something, again, we will not discuss at this moment. We will discuss it later on. I mean, very soon. So my question now is the following. Give a geometric description of the following. Description of. Okay. Span of 3, 4, 6. 2, 6, 4. Okay. When you talk about range/domain, you're talking about a function. So when you talk about the domain, it means you have a function that you're talking about its domain, and the range are the output value. Okay, which is not right now the scenario for us. Okay, span is just every vector that you can reach by following this one and that one. That's really what the span is. So it means you have 2 directions that you can move in them. The question is, what are all those vectors you can reach using those 2 directions? Okay. Okay, give a geometric description of this span. Always, step number 1, you check if they are scalar multiple. Check if they are scalar multiple. If they are scalar multiple, then it's going to be a line. So check if they are scalar multiple. Are those vectors scalar multiple of each other? Means is there a common multipliers between the component? Is there a common multipliers between the component? Okay, Haley tells me yes. No, anybody else? No? Okay. From here to here, we multiply by 2/3. Am I correct? Now, from here to here, if I multiply this component by 2/3, do I get 6? Yes or no? So if I take 4 times 2/3, I will get, of course, 8/3. So no. So what does it mean? It means that the span is the plane containing the origin, and this time, because I have value, I'm gonna write it this way to be very clear, containing the origin, containing 3, 4, 6. When I say the vector u, it means really I'm talking about contain the point 3, 4, 6, and finally the point 2, 6, 4. So these are 3 points which are not linear, and that's the span. So you take the plane that contains 0, 0, 2, 4, 6, 2, 4, 6. We're going to be somewhere here and somewhere here. The plane containing that will be the span. Means if you take anything in this plane, you can write it as a combination of those two vectors. So the minute you have to answer a question about the span for two vectors, that's what you have to check first. Step number 1. If they are not scalar multiple, and then you get a plane. If they are scalar multiple, then you get actually a straight line. Right, one more questions along those lines, which is the following. Sorry. Okay. Question is, suppose I take U to be the following vector. 1, minus 1, minus 2. And V to be 5, minus 4, minus 7. So imagine you have those two in R3 and W to be the vector 4, minus 3, minus 5. Okay. And the question is W in the plane spanned by U and V? Okay. So what does this question mean? Is W in the plane spanned by U and V? What do they mean by that? U and V, so the graphing is, as I said, in R3 become a bit harder. So U should be somewhere in here. And V should be somewhere in here. And W, I have no idea where it is. And the question is, so this is the 0. Those two vectors here form a plane. It means you take the plane that contains 0, this point, and this point. That's really precisely what this means. And now I have this vector W. And the question is W in this plane, yes or not? So how we answer those type of questions? So really, this is boiling down to ask the following. It means, is W in the span of two vectors? So to show that W is this plane, if W is this plane, it means I should be able to reach W somewhere by following U and V. So if I can reach it following U and V, it means it's in the plane span. Otherwise, W is going to be outside the plane. So is W in the plane is basically equivalent to ask, is W in the span? It means equivalent to ask, does the equation, can I reach W by following the direction of U and V? It means, does this equation has a solution? Okay, so the span of U and V is this plane containing that point, and that point. Now I have a vector W, and the question is the following. Is W outside the plane or somewhere in here? Where is W? It means basically, can I write it as a combination? If I can, W is here. If I can't, W is outside. So we solve this very quickly, and then we proceed. So solving this is equivalent to solve the system. So this is equivalent to solve the system where the augmented matrix is The coefficient of C1 are going to be the vector U. The coefficient of C2 are going to be the vector V. And the augmented term is going to be that. All right, so we solve. If we solve, and if I did that, I did it a little bit myself, granting I didn't do a mistake. I got the following: 1, 5, 4, 0, 1, 1, 0, 0, 0. So definitely that's a consistent system. It means W is in the plane. Okay. Actually, we have the following. If we solve, we get. If we solve, we get. The second row will tells me that C2 is 1. The first row tells me C1 plus 5C2 equal to 4. Back substitution give me C1 is 4 minus 5C2 equal to minus 1. It means that the vector W is actually minus U plus V. So I can reach W very easily by going a little bit the direction of minus U plus the vector V. It means that W is in the plane. Otherwise, W will be outside the plane. Okay, any questions before we start at the following section? Now, of course, what happened with 3 vectors? If I take 3 vectors in R3, can I reach any other vectors as their linear combination? And this is topic we will have to discuss a little bit slower. It's not very trivial that any 3 vectors, we can reach everything. It depends on how the vectors are going to be positioned in R3. That's how we're going to decide whether we can reach anything in R3 using 3 vectors. Any questions about the span as I move on? All right. So today's section 1.4 is basically a new notation which make writing system is much easier, and a lot of it will be rehash of the same thing we've been doing but with a different notation. So matrix equation. Matrix equation AX equal to B. So what does it mean? So what we are going to talk about is how to multiply a matrix by a vector. So the first definition is something new. What does it mean to multiply a matrix by a vector? So this is the definition of the product. Let A be a M by N matrix. M always is the number of rows, and N is the number of columns. Just to remind you, the matrix. And X a vector in Rn. And one of the main reasons we write vector in this course as a column, as a matrix like this, because I know that in your other classes, you can write them like that, a vector, 1, 2, 3, 4. You can write them in a very different way, which is fine. For us, a vector is just ordered list of number. So as long as you write them in an ordered way, it doesn't matter whether you write them this way or you write them that way. The reason we use this notation is because of the definition of the multiplication of a matrix by a vector. So we're going to view it as a matrix so we can multiply it by another matrix. So let A be a matrix and X a vector in Rn. And let A1 through AN be the columns of the matrix A. So what I am talking about, so suppose we have any matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the columns. That's A1, that's A2, and that's A3. That's what I mean by the column of A. So let A1 through AN be the column of A. It means that A is the following matrix. Then what does it mean to multiply a matrix by a vector? So what does it mean to say A times X? What's the definition? So A times X, that's A, that's X, is equal to the linear combination of the columns of A, where the weight are the entries of Xn. It means equal to X1, A1, plus X2, A2, X3, A3, plus etc. Xn, An. Okay, so X is defined so A times X, which is a very interesting definition. So A times X is defined to be the linear combination of the columns of A with weight the entry of the vector X. So A times X is defined to be a linear combination of those columns where the weight are X1 through X. So immediately example of this multiplication. Okay. So suppose I give you the following matrix. Let A be the matrix 1, 2, minus 1, 1, 3, 4. That's a 2 by 3 matrix. And X is the following vector. Minus 4, 2, and 3. Okay. So what is A times X? Defined. A times X is a vector. It's defined as follows. So that's our definition. This is A, and this is X. 1, 2, minus 1, 3, 4. So this is equal to. So this is A1, that's A2, and that's A3. So A times X is the linear combination of those. But what are the weight? The weight are the entries of that. So this is going to be equal. Minus 4 times the vector 1, 2, plus 2 times the vector minus 1, 1, plus 3 times the vector 3, 4. So A times X equal, so that's the linear combination. Now we can add them. So we're creating a new vector, and this is equal to minus 4, minus 2, minus 6, plus 9. That's going to give me a 3 in here. Minus 8 plus 2 minus 6, minus 6 plus 12. This would give me a 6. So that's the definition of A times X. Is the combination of the column where those are the weight. Example number 2. Okay. Suppose I give you V to be equal 2 times 1, 2, 3, 1. That's a vector V. Minus 4 times minus 5, 1, 3, 2. So here the vector V is in 1, 2, 3, 4 is in R4. So we've never had that. So we can always go any dimension we want. The question is a very simple question. Write V as the product of a matrix and a vector. Okay, so we're going to use the definition to write V as a product of a matrix and a vector. So can we do that very easily? What's going to be V? I wanted a product of a matrix times a vector. What's going to be the matrix? Those entries, 2 and minus the weight, are the entries of my vector. And those are the column of my matrix. 1, 2, 3, 1. minus 5, 1, 3, and 2. Okay, so this vector V, I wrote it as the product of a matrix times a vector. So now there are two important notes I'm going to address. Note number 1. When I take a matrix, I multiply it by a vector. Okay. Before I write it, let me see if you guys can answer. For this product to make sense, what condition do we need on the sizes of that? What condition do we need? So suppose I have here, you don't have to write, we're going to write it in a second. 1, 2, 3, 4, 5, 6. And the product is the linear combination of the vector. So suppose I write this, 4. Will this make sense according to our definition? Our definition is the linear combination of the column vector. So the number of entry here should be exactly the number of vectors in the matrix. So if I have 2 vectors, I should have 2 entries here. If I have 3 vectors, I need 3 vectors here. So for the product to be defined, what do we need? So A times X is defined if anybody can tell me what the condition is going to be. The number of entries of the vector should be equal to the number of columns of A. Otherwise, the condition is not defined. So A times X is defined if the number of columns of A is equal, coincide with the number of entries of the vector X. Because it's a linear combination of the columns. So we cannot have more entries than the number of columns of the matrix A. So, for example, suppose I ask you the following question. Suppose A is a 3 by 4 matrix. Start thinking a little bit. 3, number of rows. These are the number of rows, and these are the number of columns. Okay, E is a 3 by 4 matrix. X, a vector such that A times X is defined. My question is, then X is in R what? What should be the number that I have to put here for everything to make sense? Absolutely. Anybody beside Haley? I have 3 and I have 4. Which one do you think is going to be? 3 or 4? 4. Because A is 3 by 4. So these are the number of columns. 1, 2, 3, 4. So the vector here should have as many entries as the number of columns, because the first entry is the weight here, plus the weight on this, plus the weight on this, plus the weight on that. So this is definitely is going to be R4. Okay, the dimension of what we're working with is going to become more and more important as you move on throughout the course. Now, another note. Again, I want to read it, and we read it, and then I want you to see if you can give me the answer. Suppose A is M by N matrix, X a vector in Rn. So when we multiply a matrix by a vector, we are getting a vector because it's linear combination of stuff. So we're getting a vector. My question to you that A times X is a vector in what? It means how many entries the product is going to have. We start with an example and then we write the general situation in here. So on the side, suppose A 3 by 4. Okay, that's an example. And then I'll give you the other answer. And X in R4. Okay, then A times X, how many entries A times X is going to have. So this is 3 by 4. This is A. 1, 2, 3, 3, 4. And X has 1, 2, 3, 4 entries. I multiply them. I'm going to get something. How many entries I'm going to have? Think about it a little bit so we can generalize it. Remember the definition, so things will make sense. Example first. And I want in the example, Jackson, and then we generalize. Okay? In the example here. So it means if A is 3 by 4, X in R4, you multiply A by X, how many entries you're going to end up with? And then I go to the general situation. Okay, I'm getting 3. Anybody for 3? 4. Okay. Since we're not agreeing, I will work with an example till you guys see it carefully. And I will work with a 3 by 4. So I stick to the same scenario before I generalize. So I'm going to take this 3 by 4. Means I have 3 rows, 4 columns. And this is my vector X. Okay. And I multiply them. My question is, the vector I get, how many entries it has? So suppose I could call this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is one vector, my second, third, and fourth. I multiply by a vector X, which has 4 entries. Otherwise, it doesn't make sense. So let me call those entries X1, X2, X3, and X4. I multiply them. The product is a combination of those vectors. So it's X1 plus X2 plus X3 plus X4. The resulting one, how many entries is going to have? 1, 2, 3, this have 3 entries because a linear combination of those. This one have 3 entries. This one have 3 entries because each one of them have 3 entries. 3 entries. So when I'm going to add them, I'm going to have 1, 2, 3 entries. So A times X is going to be a vector in R3 because I'm going to have 3 entries. I stop. Is that clear why it is 3, not 4? Because it's a combination of the column. Each one of them have 3 entries because at 3 by 4, it means the resulting one will have 3 as well. So what's going to be the answer here in general? So you take a matrix, it's M by N. Means here I have N entries. Fine. But every vector here have M of them. So here M entries. This one have M entries. This one have M entries. So their linear combination is going to have how many entries? What shall I write here? N or M? Absolutely M. Because this has M, I'm adding to this one M, and this is going to be M entries. So when you are multiplying a matrix by a vector, we have first we get a vector, that's what we get, and how many entries it will have, because you're taking linear combination of the columns, you will have the same entries as you have in the column. All right, so the product is defined, 2 things when we're multiplying. A times X is defined if the number of columns of A coincide with the number of the entries of the vector X. When you multiply them, you get a vector which should have as many entries as each vector in the matrix A has. Part 2 is along the same line, but there is an equivalent definition of the product. So we saw one definition. I'm going to introduce immediately the other equivalent definition, which does not give you a meaning for the product, but it's easier to use if you're only interested in computation. So an equivalent definition of the product of a matrix and a vector. It's called the row column definition. Okay, so that's another definition called the row column definition. And let me elaborate how it works. So this is my matrix A. And this is my vector X. And we are going to multiply them. And you're going to see, once we multiply them, we're going to look at them in a different way. So what is the definition I gave you? This is equal to x1. So I'm not changing the definition, but we're going to look at it in a different point of view. Times 1, 2. Plus x2 times minus 2, 4. Plus x3 times 3, 7. So that's our definition. It's a linear combination of the columns of A, where the weight of the linear combination is x1, x2, and x3. That's exactly the definition. All right. Now I'm going to, so this is, we're adding vectors, so let us add them. So this is x1 minus 2, x2 plus 3, x3. I am adding the first row. Now I'm going to add the second row. 2, x1 plus 4, x2 plus 7, x3. Am I doing anything different? I'm just following the definition before. And now I'm going to look at this in the following way. So I'm going to hide a little bit the second row here. Right there. And I'm going to analyze the first row. How did we get the first row? The coefficient of x1 here is the 1. The coefficient of x2 is minus 2. The coefficient of x3 is 3. So you can think of the first row as we got it like this, and that's where row column definition will come from. 1 times x1 minus 2 times x2 plus 3 times x3. So that's what we're getting for the first row. So that's the equivalent definition. Row column x1 minus 2x2 plus 2x3. That's the first row. The other one is exactly the same. The x1 is obtained by taking 2 multiplied by x1. This is obtained by taking 4 by x2 and 7 by x3. So the second row is going to be 2x1 plus 4x2 plus 7x3. So that's what the row column definition is coming from. So you can think about it as you're taking this row, multiplying it by this column, term by term, term by term, term by term. Does this remind you of anything you guys have done in 261, some of you? Does this remind you anything you guys have done in 261? It's like dot product. You can think of it as a dot product. You can think of this as a vector and this is a vector, and you take in the dot product, x1 minus 2x2 plus 2x3. You move down, 2x1 plus 4x2 plus 7x3. So one way you can think about that is that you're taking dot product of this row vector and this column vector. So that's an equivalent definition. This one we use a lot when we are computing, when the meaning is not really important for us. The first definition give me an interpretation of the product. This is just give me a way to compute. So let us take an example. Perform the following product in 2 ways. in two ways. Basically, I want one is using the definition, second, the row column definition. So I'm going to take this matrix, 1, 0, 2, 3, and minus 1. I'm just making up numbers, 1, 2. And I'm going to multiply it by a vector. Now, because I have two columns, I only have to have two entries. Otherwise, the product will not be defined. And then I'm going to do it in two ways. Of course, you're going to get the same answer. The first way is use the definition. It means as linear combination. That's what I mean by the definition. The second, I'm going to use the row column. Okay, let's do the first one. It's 2 times, that's the entry, the linear combination times the vector, 1, 0, 2, 3. That's why we're going to get a vector in R4, plus 3 times minus 1, 4, 1, 2. That's our definition. Now we can add them. You have two vectors. You can add them if you want. And this would give me 2 minus 3 minus 2. Sorry, 2 minus 3 minus 1, 12. 4 plus 3, 7. And 6 plus 2, give me 8. So that's the usual definition. Now the row column. How does the row column work? Okay. All right, we start the first row. Row column. 1 times 2 plus minus 1 times 3. I'm just doing it the slow way. Then I move 0 times 2 plus 3 times 4. That's the row column. Then I move down. 2 times 2 plus 3. And finally, 3 times 2 plus 3 times 2. I did a mistake somewhere. 2 times 3 is 6. 6 plus 6. Sorry, that should be 12. Plus 3 times 2. Finally, I will get the following. 2 minus 3 minus 1. 12. 4 plus 3, 7. 6 plus 6, 12. Of course, they are the same, but with a different point of view. Easy for computation. If you don't care about the meaning, this will tell you the meaning of the product. What does this product represent? Okay. Any questions so far? What I think we're going to look at is the matrix equation AX equal to B. Right. The question is, solve the equation AX equal to B. So before we talk about that, it's because it will be simple. When you first learn multiplication back in middle school or wherever, and they define the idea of 2 times 3, what does mean, which is equal to 6. And then the first thing you do is you tell you, okay, solve the equation 2x equal to 6. So it means basically, you have to find the x such that you multiply 2 by it, you get a 6. So now we define something called multiplication of a matrix times a vector, which is multiplication at a higher meaning. And the question solve the equation AX equal to B. So it means, what does this mean? It means the following. X is my unknown. And I need to find x1, x2, x3, such that when I multiply this by that, I get the vector 1, 3, minus 1. Okay, that's what it means, solve the equation AX equal to B. So now you can just follow the definition. So this means, what do we have to solve? You either use the linear combination to evaluate this product, or you can use the row column. So if I use the row column, I get x1 minus x2 plus 0 to x1 plus 2x2 plus x3, and then 3x1 plus 5x2 plus 4x3 equal to that. So I need to solve this. I need to find the x1, x2, x3 such that this product give me that. It means equivalent to solve that this vector equal to that. So basically, this is equivalent to solve the following system. So everything take us back to system with a different point of view every time. Equal minus 1. So now we just have to solve the system. We set it up and we look at it. It's 1, minus 1, 0, 1, 2, 2, 1, 3, 3, 5, 4, minus 1. And now it's needless to say that what is the augmented matrix? 1, 3 minus 1 is nothing more than the vector B that we are after. That's the vector B. And this matrix here, again, the coefficient of x1 are the vector 1, 2, 3. The coefficient of x2 are this vector. The coefficient of x3 are that vector. So this is nothing more than the matrix A. So solving Ax equal B basically means solving the system where the augmented matrix is AB. A is the coefficient, B is the constant term. And now we can solve this the usual way. And we get the following. 0, 0, 1, minus 3, and 0, 4, 1, 1, and 1, minus 1, 0, 1. And now we solve using back substitution. Give me x1, x3 equal minus 3, back substitution. x2 would be, this one read 4x2. I did not finish, so that's okay. Plus x3 equal to 1. It means 4x2 is 1 plus 3, so x2 is equal to 1. And x1 is 1 plus x2, x1 equal to 2. So the solution, and we're going to write it in vector notation because I'm looking for the vector x. So the solution is 2, 1, minus 3. So nothing new at all. The only new thing is that the idea of solving the equation Ax equal to B. So we introduced this new notation Ax equal to B, and now we talk about solving the equation Ax equal to B, means looking for the vector x when you multiply it by A, you get B. And it's really boiling down to solve the system where the coefficient with the augmented matrix has A as a coefficient and B as the constant term. Okay, I think I have to stop right there. Any questions before I let you go? Okay, as I said, I hope to be back by February 11, and you guys will have your quiz 1, quiz 2 on that day. And your quiz, one of you asked me, it's going to be basically based on everything we did. I mean, from echelon form to reduced echelon form to pivot to solving a system to span to linear combination, and what we are going to do right now. And I will give you more information as you move on. Okay, any questions before we're done? Okay, please do your homework. Make sure to do them because the concepts are going to become more and more concept easy, but a lot of concepts. Okay, any other questions? Okay, bye guys, and see you next week.